Hi, my name is Alex Alford. I'm the treasurer for the University Secular Society, and today I'll be giving a talk on the universe and our place in it. But before I get to those details, something I want to start out with is this idea that as a non-religious person, you can't really have any meaning in the universe, or that your place within it doesn't matter at all. And while it may be the case that there may not be inherent meaning, I think that from a secular perspective, you can find one for yourself, which is why personally I subscribe to an idea called optimistic nihilism, which is this idea that while things may not inherently matter, it may not be written on a stone tablet somewhere or given to us by some god, the fact of the matter is there's still a lot out there for us to learn, and there's a lot out there for us to do, and there are people we care about. And I think the fact that we are here and that we are so lucky to be here is good enough reason for us to continue chugging on and to live this life while we have it. And going from there, let's talk about where everything all started. Let's go over to the Big Bang. So a very common misconception, especially because of the name, is that the Big Bang is just some explosion in the universe. It was some big crash or boom, and everything, including our planet, just came flying out of it. But the reality is, as you can see here, is that the Big Bang is actually the universe itself expanding. So the idea was that the universe began as an incredibly small point, what they would call a singularity, but probably isn't a singularity. The reason they specify is because it'd be infinitely dense, so it probably means there's a problem in the math somewhere, but the whole point is they labeled a singularity. It's incredibly small, and so it was in this very, very hot, dense state, as the intro of the Big Bang song may have said. And for whatever reason, it ended up rapidly expanding from where it existed. And from there came everything that we hold and know dear. And so there were multiple stages after that initial expansion. The earliest stage that existed that we pretty much don't know anything about and may never know is called the Planck Era, which was around 10 to the negative 43 seconds before the Big Bang occurred. And that right there, if you forgot how to do, scientific notation, that is a 0 point with 43 zeros trailing and a 1. It's an incredibly, incomprehensibly small amount of time. In fact, it's called the Planck time because, like the Planck length in physics, it's the smallest unit of time that seems to make sense to talk about in physics. So before that era, or around that era, we don't really know what happened, but very, very, very incredibly shortly after that was what was known as the Gut Era, or the Grand Unified Theory Era. And that was around 10 to the negative 38 seconds later. Again, an incredibly small difference, so less than a blink of an eye. And it's called the Grand Unified Theory because at this period of time, pretty much all the fundamental forces, except for gravity, were united. So the four fundamental forces are the electromagnetic force, gravity, the strong and weak nuclear forces. And so the strong and weak nuclear forces and the electromagnetic force were united somehow. And so it lasted for that amount of time, being very, very brief, staying that way. And then after that, we had the Electroweak Era, which was 10 to the negative 10 seconds afterwards. And again, incredibly, incredibly small. I mean, you just imagine like, we call that an era, but I mean, it's nothing pretty much, but it still occurred. And so within that era, that's when the strong nuclear force finally decided to split, break away from the other forces. And so then you had the electroweak force, which was a combination of the weak nuclear force and the electromagnetic force. And that persisted for quite a while until you had something a bit more consequential called the particle era, which is a much more reasonable and imaginable amount of time, but still not comprehensible, which was 0.001 seconds after the Big Bang. And during this era, that is when we finally started seeing quarks. And quarks are these particles that are what make up protons and neutrons, the things that make up everything around us. And like you may have learned in chemistry, a plasma is basically a sea of atoms with electrons freely moving about. And so a quark-gluon plasma is all these quarks, but instead of being connected and bound together by these other smaller particles called gluons, it's now a sea of quarks with everything freely moving about instead of being bound to each other. So in that way, it's analogous to plasma. And so we didn't have any hydrogen or helium or really anything, just a sea of quarks. And it persisted that way for quite a bit. So there's a couple eras in between here and now, but let's immediately jump to a more familiar place, 500,000 years after the Big Bang. And this is when we actually start to see the first stars forming because we have helium and hydrogen which formed as a result of the Big Bang. And so in that era, we see our first generation stars, which are the purest stars you could ever have, only made out of hydrogen and helium. And there's something very interesting about acknowledging that fact. I mean, where's everything else? Really, the only other thing that was there, aside from hydrogen and helium, was lithium and a couple isotopes of hydrogen. Where's all the iron, the gold, the silicon, the carbon, or really everything in our planet? It seems like it's just nothing but the gas we use in balloons. So let me transition to something, and this will be of relevance, as you'll see. Let's go to the human body. So the human body is composed of a lot of different things. We're composed of 65% oxygen, 18% carbon, 9.5% hydrogen, 1.5% calcium, and the list goes on. And of course, we have a lot of trace elements that we're made out of, including iron in our blood. And so you have to ask the question, where did all that come from? If the first thing that came out of the Big Bang were these elements, what process could have formed that? Well, there's a quote I really love. It's one of my favorite quotes by Carl Sagan, which is, "We are made of star stuff." And so there's this process stars undergo called stellar nucleosynthesis, which is when, over time, from all the pressure that is happening in the core of stars, elements are forced to fuse. So going to another misconception, a lot of people think of our star, the sun, as like a big ball of fire. Now it does have plasma, and there is bits of plasma in fire, but it's not the same thing, because fire would require oxygen, a fuel source, and it would also require heat. I'm sure my Boy Scouts would know the fire triangle. But with the sun, we don't have that. Well, there is oxygen, but it's not necessarily fire, and the first stars didn't even have oxygen. So what's generating all that heat, that unimaginable heat and radiation? Well, it's all the gravitational force pushing this ball of gas together, and in the core, it's literally forcing the hydrogen atoms to fuse with one another, releasing a lot of energy. And so what stellar nucleosynthesis is it's a chain. It starts from hydrogen fusing into helium, and from there it keeps going. As you can see here, it goes from hydrogen to carbon to oxygen to neon to magnesium to silicon until inevitably, like all of us humans will have to face, things start to break down. We get slower as we age, and well, what happens with stars is that as they finally start forming iron, well, they basically receive their death sentence. Iron is so hard to fuse into a heavier element, to fuse two hydrogen atoms together, that the star can no longer keep itself afloat. So normally, something that massive would compress in on itself, maybe forming a black hole, or maybe compressing so quickly that it bounces off the core. And I'll explain kind of how that relates to stars in a second. So all that force from the radiation happening in the core is what's fighting back gravity from keeping it from completely collapsing. And so once it reaches iron, it can no longer produce all that radioactive pressure. It can't produce all that energy. And so inevitably it reaches the end of its life in multiple ways. So for your average star, they eventually get older, bigger, and red, become a red giant, and then from that point, they kind of just fizzle out, where the outer shell is kind of dispersed and it becomes a planetary nebula, and what's left is a white dwarf. Something that's not really a true star, it's more like a core that's still super hot. And you have to think, if your only source of getting rid of that heat is expelling radiation into the endless void, it's going to be a very, very long time until you cool down. Or, the more beautiful and cataclysmic event that could occur is that the star itself could end up imploding, and then the rest of the shell bouncing off the core and exploding in a very amazing explosion, one that would dwarf anything humanity could do with nuclear bombs, one that would trail out for multiple light years, one that would scorch planets and destroy everything in its wake. But the beautiful thing from this chaos and this destruction is that this star is spilling out its guts everywhere. And so what does that mean for humanity or other organisms? What does that mean for planets? That means that these elements return to a big gas cloud, maybe a planetary nebula, or just a regular stellar nebula. And eventually, one day, gravity will allow those things to compress and form planets like ours. And then those same elements one day will go on to be part of our body. And so everyone in this room has elements. You have atoms within you that came from stars billions of years ago. And these elements are only here because those stars paid the price and died. And maybe some of us had atoms that shared the same star. Who knows? But in some way, that makes me feel a little interconnected with the universe. Almost instills a spiritual-like feeling in me. Not this idea that there's this higher magical or metaphysical type power, but just that in a way, what I am and what I'll be will always in some part be around. Maybe I won't be conscious, but it's going to be somewhere, and it was somewhere. So now, moving from there, let's talk about our place in time and space. Now, we occupy an average star in an average corner of the galaxy, and while we might be able to live there, it's obviously not that perfect. And the thing about humanity is that we really, really, really like to prop ourselves up. In fact, for the longest time, there are people who would kill you if you didn't say the sun was revolving around the earth. We viewed ourselves as the center. We viewed ourselves as untouchable, and in many ways we still do with the way that we destroy so many ecosystems and how we view ourselves as basically the apex above everything. And in fact, we even compare intelligence of other animals by using a word called sapience, from sapien, Homo sapien. We're definitely very human-centric, and that's probably just a consequence of evolutionary biology. But after I go through this, maybe it will knock you down a couple pegs. Because if you really think about how massive everything is and how small we are in comparison, both in time and space, you'll see that in the grand scheme of things, we're really nothing, for good or worse or neutral. So let's get a sense of scale. Let's start somewhere very local. Take our sun, our beautiful star that we look at every day and is oftentimes blinding us on the way to work. Our distance to the sun is around 93 million miles, which is a crazy, unimaginable distance to think about, but even though it probably still won't help you much, one way that we could also define that is, we could define that as walking around the Earth 4,558 times. That's how far away the sun is from us. But let's not just talk about distance, let's talk about how big it is compared to the Earth. If we were to shrink the Earth down to a grain of sand to get a sense of scale, which would be around 0.5 millimeters, we would find that if we were to scale down the sun to the same size, the sun would be around 7 feet in diameter. So imagine a ball 7 feet in diameter compared to this very, very, very tiny grain of sand. But it doesn't just stop there. If we take how far away the sun is from the Earth and we try to scale that down to those sizes too, the Earth would be 19 feet away from the sun. So imagine a ball in this room, maybe about as long as this room or longer. Well, not a ball, but the length. Imagine that ball on the other end of the room at 7 feet in diameter, and then you have a grain of sand 19 feet away. And that would be how far away the Earth is from the sun, from that perspective. Which is really crazy, but if we go a bit further with that, if we extend this comparison, let's talk about the Milky Way. So first let me say that with the Milky Way, I think we tend to have this perspective that all the stars in the night sky are really most of the Milky Way, but the reality is that just isn't the case. With our naked eye, we can really only see around 0.00003% of the Milky Way, which is an incredibly small sliver from the human perspective. And in some ways, it kind of makes me feel a little sad knowing that all these great pictures that we get from the Hubble Space Telescope and others were not able to be accessed to those who came before us for so long. Everyone looked up and thought that's all there was, when really we know that there's much more than that. So much more that we could never comprehend it. And so, extending our earlier comparison, the Milky Way is around 100 billion light years in diameter, which is really crazy. I mean, the speed of light is around 300,000 kilometers per second. And it would take that same light 100 billion years to traverse the Milky Way. I mean, think about that. Think how much distance that is. 300,000 kilometers a second. How many seconds are in 100 billion years? So if we were to compare that with the grain of sand now, and we were to scale it down proportionally, the Milky Way would be around 24,000,000.3 miles in diameter. So that would be about 1/5 the distance of the sun. So, imagine a ball that big. It's 1/5 the distance of the sun in diameter compared to a grain of sand, and that's the Earth compared to the Milky Way. It's nothing. It's barely anything. It's like atoms, those things we can't see but make up everything. Well, can't see with the naked eye. But so going from there, I'd like to continue this discussion, but first let's talk about some very crazy numbers that might drive this home. So first one I really like is the fact that the observable universe is 93 billion light years in diameter. And we're not going to extend the grain of sand analogy because, well, that would probably be fruitless considering how big that number would be. But I guess if we're going to talk about miles, it's around 5.4 times 10 to the 23 miles. Again, 5.4 with 23 digits trailing it. And if we talk about our place in time, the universe has existed for around 13.8 billion years, and humanity's only been around for 200,000 years. That's how small we are in time. That's nothing. That's 0.0014% of the universe's existence. But that percentage is going to get even larger because inevitably one day humanity will die. Humanity will be gone, as bleak and grim as that sounds. It's just an inevitability. And one fate that our universe will eventually face is the heat death, where all the energy in the universe is eventually evenly dispersed to everything. And so there will be such small amounts of energy available to everything that nothing can ever happen again. In fact, atoms won't even be able to exist. The energy will be so low that not even they can sustain themselves. It would be nothing. It would be unrecognizable. But that's a crazy amount of time from now. That is 1.7 times 10 to the 106 years from now. Try writing that on your piece of paper, a piece of paper in front of you. 106 digits. That's how many years from now that is. But of course, it's still not an infinity away. It's still an inevitability the universe won't escape. And then also, if we talk about the number of galaxies, so our galaxy, think about how big that is. But a lot of astronomers estimate that at the bare minimum, there's at least 100 billion galaxies, and maybe up to 200 billion within reasonable estimates. And so because of that, that also means the number of exoplanets is practically uncountable. With all the planets that we keep finding, a lot of astronomers are starting to think that on average, a star has at least one planet. And so because of this, in our galaxy alone, there may be around 1 or 10 billion planets in our galaxy alone. How many of those are habitable, we're not sure, but that's a really crazy number. And if you scale that up to the universe itself, estimates put it around 700 quintillion planets. And so oftentimes we again try to think of ourselves as alone in this cold and dark universe. But it's pretty unfathomable to think that within that great stretch of universe and that many planets, that there's not at least bacteria or something on another planet, that there's not life elsewhere. Maybe there's none in our galaxy, but there's so many galaxies to choose from. Maybe one's in another. And so we kind of need to outgrow this human-centric idea that we are everything, that we are all, that the universe is centered around us, because it's really not. And so transitioning from that, let's talk about where we may be going, where not just humanity, but our solar system and the universe itself may be going. There's multiple ways in which at least our world, the Earth, could end. People talk about how perfect everything is for us, and while it is the case that we are very lucky to be where we are at this time and place, the reality is that life is quite fragile. We've only been around for around 200,000 years on a planet that's existed for a couple billion years. And there have been many who've come before us, many species, that have been wiped out from threats from the cosmos like asteroids, or have been wiped out through other disasters like volcanoes erupting out from the planet. And so there are numerous ways in which all this could end even right now. So, not to scare you, but I think going through these will give you an even greater appreciation of where we are. And maybe if you're struggling with having purpose, maybe it will make you realize that we have to use this precious time while we have it. So let's throw out a figure about asteroids. Only around 3% of the sky right now is being monitored for them. And so that means that there are plenty that could be weeks, maybe days, maybe hours away. And we might not catch it before it's too late. And, well, the dinosaurs met that same fate. Just because we think so highly of ourselves doesn't mean that we can't. And it would be so easy, too. I mean, one the size of a city would wipe out the entire planet, sending dust bowls worse than what we could have ever imagined across the entire planet and causing many volcanoes to erupt and tsunamis worldwide that would drown everything. But that seems a lot more tangible. There's threats from further away that are a lot less tangible and a lot less predictable. Take, for example, gamma ray bursts. So sometimes stars go through this very energetic event where near their poles, their magnetic poles, they shoot out jets of gamma radiation that's very, very, very powerful, that could sterilize entire planets from light years away. And so if they're angled just right, they could hit our planet. And think about how many stars are out there. It'd be like a cosmic sniper light years away that we wouldn't have known about, especially considering gamma rays are light, so we wouldn't know until it got here. Maybe we could predict that the star might do it soon, but we wouldn't see it until it's actually here. If we're lucky, maybe it would strip away most of our magnetosphere and maybe give a lot of people sunburns, but in the worst case scenario, it would wipe out everything, maybe except for some archaebacteria. But then there's even stuff even less tangible and maybe a bit more scary to think about. So a lot of particle physicists think that this very fundamental particle called the Higgs boson could wipe out everything as we know it. So the Higgs boson is responsible for a lot of things, many of which that I'm not qualified to talk about, so I won't do that. But what I will say is that it's so fundamental that sometimes it's nicknamed the God particle. And so what they've said about this particle is that it may be the case that it could change in a way that would lead to all the physical laws changing, which would effectively destroy everything. So if we think about energy states, or potential energies, we can think about a hill going down like this, maybe another hump. So something might have potential energy by being near that edge of the hill, and then eventually it uses that and falls and gets straight into this comfortable spot. Everything in the universe wants to move towards a more comfortable state, a place where it's more stable, which is why certain atoms, man-made ones, like element 118, can't really exist for very long because it's unstable, and so it ends up decaying into lower mass elements. So there's the same principle behind that. Well, some physicists think that the Higgs boson might actually be unstable. Then it might only be in a temporary little pocket over here, or nook, cranny. And there's actually another little hill, a potential energy, and that if it jumps up and falls back down to where it wants to be in a new energy state, that something called a false vacuum decay would occur, where a bubble spreads out the speed of light, and everything in its path would have its physical laws rewritten. And if that were to happen, that's another thing that we really wouldn't know until it got here. I mean, one could start right there, here, there. I mean, it could start for you, the viewer, at home. But if we're lucky, because our universe is expanding, if one did happen and it was near the edge of the observable universe, then it would be the case that we could actually miss it, because the universe is starting to expand, or is already expanding, faster than the speed of light. And so basically you'd have this infinite bubble traveling, and us infinitely getting further away from it. So we might get lucky in that regard if it were to ever happen. And if it worries you a lot, maybe you'll take some consultation in thinking that particle physicists really aren't settled on this. This may not be a thing that can happen. They don't know whether or not it is unstable. Just more so that if it is, then at some point this will have to happen. But maybe there isn't an end as we would think about it. Another idea, which comes from Roger Penrose, a man who worked with Stephen Hawking, the late Stephen Hawking, is one I really like, and it's called the Big Bounce model. And it comes after this idea that the universe is expanding very quickly, and then maybe eventually it will slow down, and then eventually it will reverse. And so what happens is called the Big Crunch, where it goes back into that primordial state it was in, that singularity. And so maybe for an infinite amount of time, if the Big Bounce model is correct, maybe it quote-unquote bounces back, where Big Crunch happens and then another Big Bang, and this happens forever. And I feel like this raises a couple existential questions that I sometimes think about, which is, I believe in an afterlife. I personally don't believe in a God. But maybe if the universe does exist infinitely, and there's all these different combinations for infinite amounts of time, maybe what I am or was, maybe that will eventually reassemble itself. And maybe it wouldn't be me, or maybe it would be and I would have no memories of some previous existence. But maybe in that sense, reincarnation might exist. Though that's just speculation, and we probably have no way to really know. But I guess in that sense, that would be a plausible way through physics that it could exist, and not necessarily this idea that your soul is transferred to some thing. And so with that, I think one thing that you really need to let sink in and hold dear is that life is very, very incredibly fragile. And tying things back together from the beginning, there may not be an inherent meaning to anything, and maybe we'll never find it. But when we look out in these vast stretches of universe, we see that not only are there still many mysteries, many things we don't know, but we see that so far in our search, there isn't any life. And while it's very probable life exists out there, maybe this idea that life is so scarce, maybe that should mean to us that there might be a good reason worth preserving it. Maybe we might want to exist as long as we can, this almost magical-like experience, this limited amount of time we have left. I mean, in a way, we're part of the universe observing itself. I mean, how odd is that to think about? And so I think that with that, I would say my meaning is to not only do well by those who I know and by the rest of humanity, but to try and pursue knowledge, which is why I'm currently here at USM studying as a physicist. Maybe while these mysteries are still out there, and maybe we're the only thing that can think about them, maybe we should try to be the ones to overturn every stone. And with that, I thank you for my time speaking, and I hope that changed your perspective on the world, maybe just a little bit.